Hello everyone and welcome to a new lesson, which is the merge sort. In this lesson, we are going to find out what is merge sort, how does it work, and then we are going to analyze the time and memory complexity of the algorithm. So let's start. What is merge sort? Merge sort is an efficient, comparison-based, and stable sorting algorithm. So, what does efficient mean? It means that it is run in the optimal time complexity possible of sorting an array of objects, and that is big O of n log n. What does comparison-based mean? It means that it is based on a single abstract comparison operation which determines which of two elements should occur first in the final sorted list. Some examples of these operators are less than or equal to, less than, greater than or equal to, greater than, and so on and so forth. Note that these operators could be even customly defined. For example, when we want to sort an array of two-dimensional points, we might define the less than or equal to operator as the principal by abscissa and then by ordinate. And last but not least, stable means that the order of equal elements is the same in the original and in the sorted list. Next question, how does it work? Well, it uses a divide and conquer approach. Divide and conquer recursively breaks down a problem into two or more sub-problems of the same or related type until these become simple enough to be solved directly. The solutions that we find to those sub-problems are then combined to give a solution to the original problem. So whenever we want to design a divide and conquer algorithm, we must answer two questions. First one is what are the sub-problems? And the second one is how to combine the sub-problem solutions in order to get the originals one. In our case, the original problem is that we are given an array of integer nums and we have to sort it. What do you think are the sub-problems to this problem? The first one could be to sort only the first half of the array, and the second one would be to sort the second half of the array. So let's suppose that we have solved each of these two sub-problems. Is the array nums sorted? Not yet. Remember that we have to answer a second question when it comes to divide and conquer approaches, and that is how to combine the sub-problem solutions in order to get the originals one. Well, what is to be done here is that we have two subarrays that are sorted, and we need to merge these sorted subarrays into the bigger one. Does this sound any familiar to you? Remember that we have already solved this problem in a previous lesson. So take your time and feel free to go to that previous lesson and remember the approach before continuing with this one. And then let's put that algorithm to action. Let's see how it is going to merge these two sorted subarrays into the whole sorted subarray nums. We are starting with two pointers, each of them at the beginning of each of the two sorted subarrays. And as long as we haven't placed all the elements into nums, we are going to see which of these two current elements is the smaller one. Here, 1 is less than 3, so nums of 0 is going to be 1, and the purple pointer will move to the right. 3 is less than 6, so nums of 1 equals 3, and the green pointer is moving to the right. 5 is less than 6, so the next element in nums will be 5, and the green pointer moves to the right. Now 6 is less than 7, so the next element is 6, and the purple pointer moves to the right. 7 is less than 8, so the next element is 7, and the green pointer moves to the right. 8 is less than 9, so the next element is 8, and the purple pointer moves to the right. 9 is less than 10, so the next element is 9, and the green pointer moves to the right. And because there are no more unprocessed elements in the first subarray left, we will push the remaining elements from the second subarray one by one, so the next element is 10, and we are done. And the whole array nums is now indeed sorted. Now let's see a little bit how this algorithm looks like. Usually, when implementing divide and conquer approaches, we will use a recursive function. So let's define the recursive function named merge sort, which takes three arguments, nums left and right, and sorts the subarray nums from left to right in place. Inside the function, we will have to split this subarray into two halves. In order to do that, we first have to compute the middle position, which is equal to floor of left plus right divided by 2. Now, we have to solve our subproblems. So first, we will sort the left half. And for doing that, we will call merge sort of nums left and middle. Then we will sort the right half. And for doing that, we call merge sort of nums middle plus 1 and right. And finally, we need to combine these two solutions. And for that, we will implement another function which is called merge subarrays and takes 4 arguments, nums, left, middle, and right, and it merges the two sorted subarrays, nums of left and middle, and nums of middle plus 1 and right, into the subarray nums of left and right. If you can't think of a way of implementing this function, make sure you go to the previous lesson of merging two sorted arrays, and completing again that coding tutorial should be enough to be able to implement this function. Now, having these functions defined, all we have to do is call merge sort of nums and 0 and n-1, and when this call terminates, we will have the whole array nums sorted. But there is one problem with this algorithm that you might not have noticed. The merge sort function calls itself forever, so the algorithm actually never stops. One more thing that we really need to be careful at is that whenever we implement a recursive function, we need to define well the stopping point. This stopping point actually represents those subproblems that became so simple that they are already solved. And those subproblems are those subarrays which only have one element. Or in other words, left equals right. And that is because the subarrays which only have one element are already sorted. So all we need to do here is, before computing the middle position, checking if left equals right. And if so, stop the function. And this is the final algorithm. Now let's take an example to understand better how it works. Let's say this is the array nums that we need to sort. We are going to call merge sort of nums and 0 and 7. So the left pointer equals 0 and the right pointer equals 7. Inside this function call, we compute the middle position, which is 3, and call the function for the subarray nums of 0 and 3. Inside this new function call, we compute the middle position, which is 1, and call merge sort for nums 0 and 1. Again, compute the middle position, which is 0, and call merge sort of nums 0 and 0. And here we hit our first stopping point. Left equals right equals 0, so this subarray is already sorted. We stop this function call and get back into the parent one, where we will call merge sort of nums 1 and 1. Again, left equals right, so this subarray is already sorted, and we stop this function call. We go back into the parent call, where there is one more thing to do, and that is merge these two halves into the bigger subarray. Now the subarray nums of 0 and 1 is sorted, and we will also end this function call. We go back into the parent call, where remember left equals 0, right equals 3, and mid equals 1. And we are ready for step number 2, which is calling the merge sort function on the subarray nums of 2 and 3. Inside this call, we compute the middle position, which is 2, and we call merge sort of nums of 2 and 2. Left equals right, so this subarray is already sorted, so we will stop this function here and return to the parent call. Now in the parent call, we proceed to the next step, which is calling merge sort of nums of 3 and 3. In this call, left equals right, so again the subarray is sorted, we stop the call and return to the parent one, where we proceed and do the last step, which is merging these two together. And we get the subarray nums of 2 and 3, which is now 7, 9. Now this function call has also terminated, so we return to the parent one, where we proceed with the last step, which is merging these two halves together, and now the subarray nums of 0 and 3 is also sorted. This call is also terminated, so we return to the very first function call, where we proceed with the next step, which is calling merge sort of nums of 4 and 7. The middle position is 5, and from now on you can imagine what happens. We will continue in the same fashion that we did in the first half, and when this function call will finally terminate, we will also have the second half sorted. We are again back in the parent call, where we only have to merge these two halves together, and we will get the whole array nums sorted. Alright, so we have seen what is merge sort, how it works. Now we have to do one more thing. Analyze the time and memory complexity of the algorithm. In order to do this, we have to take another look at the actual algorithm. So let's see the function again. First, we have an if statement, and then we stop the function if that condition is satisfied, so this is constant time. Then we compute the middle position, which is also constant time. Then we have two more function calls, but we won't analyze this here, because we are interested in seeing what is the time complexity of one specific function call. So everything that function call does, besides calling itself. And finally, we call the merge subarrays function, and we should remember that merging two sorted arrays of lengths n and m respectively takes a total time complexity of big O of n plus m. In our case, we are merging two subarrays which have lengths equal to middle minus left plus 1 and right minus middle respectively. So the total number of operations performed to merge these two subarrays is right minus left plus 1. This means that the total number of operations that one function call does, again not taking into consideration what is performed inside the function calls that are done in this function call, is equal to the actual length of the subarray, which is right minus left plus 1. So what we care about is what function calls we perform, and more specifically, the lengths of the subarrays that this function is called upon. The original call is merge sort on the whole array, so on a subarray of length n. Then we call the merge sort on two subarrays of both length n divided by 2. Then from both of these calls, we call the function two more times on subarrays of length n divided by 4. Then for each of these 4 calls, we call the function two more times on subarrays of length n divided by 8, and so on and so forth. In order to get the total number of operations performed by the algorithm, we need to add these lengths together. From the first call, we get an n. Then from the next 2 calls, we get 2 crossed n divided by 2. Then from the next 4 calls, we get 4 crossed n divided by 4, plus ... plus on level k of the recursion tree, we get a 2 at power of k crossed n divided by 2 of power of k. As you can see, all of these parentheses are actually equal to n, so the total number of operations is k plus 1 crossed n. But because we can't express the time complexity depending on k, because we don't know who k is, let's see what is its value. This is simple. Remember that we split each subarray in 2 halves, until at some point these subarrays have a length equal to n divided by 2 at power k. So this 2 at power k couldn't exceed n, which means that k is log of n. And the final time complexity of the algorithm is big O of n log n. And because we do everything in place, not using any extra arrays, the memory complexity of the algorithm is big O of n.